start by giving back the exams. I did get them done. Talking about intermolecular forces, we haven't been particularly chromatographic yet about where they come into play, but we will. It should be obvious that intermolecular forces are responsible for retention in chromatography. And the different kinds of intermolecular forces, which we've already introduce different kinds of chromatographic selectivity. That's why we have to get into some of these details. And I mentioned already, we talked about a bit, the so-called dispersion forces. These are the most general kind of force. No matter what you're dealing with, even 2 helium atoms, they are bound to a certain extent by weak dispersive interactions due to the transient dipole interaction. Dispersion interactions are very short-ranged. They go with 1 over r to the 6th. We also talked about permanent dipole interactions, also called Keeson interactions, also called orientational interactions. When we account for the fact that the dipoles are spinning around very rapidly, these two also depend upon 1 over r to the 6th, but they get weaker as we increase the temperature. So as we raise the temperature, these dipoles are spinning more rapidly, and the average interaction gradually goes off to 0. So they decrease the higher the value of kT. I don't think we got quite this far the other day. Dipole-induced dipole interactions, also called the Debye interactions, and we will certainly talk about hydrogen bonding and Lewis acid-base interactions today. So with that, let me now race forward to the permanent dipole-induced dipole interaction. Right off the bat, we see once again that they're short-range interactions. They go with 1 over r to the 6th. They don't depend upon kT. And they're not much influenced by the angle of one dipole relative to the polarizability of the other molecule. The net induced force or energy depends upon the polarizability of molecule 1 and the dipole moment of molecule 2. So it's the dipole of this interacting with the polarizability of this that gives you one part of it. Now, if molecule 1 is also dipolar, and something can be polarizable and dipolar at the same time, then molecule type 1 can induce a dipole in molecule type 2, so it's the sum of these pairwise interactions that gives you the net induced energy of interaction between the 2 molecules. And if you think about it, if we're talking about the net total interaction, we have to add up the dispersion interaction, the dipole-dipole, the permanent dipole interaction, and the permanent dipole-induced dipole interaction to get the total energy of interaction of simple molecules. So there's 3 different components to what can hold these simple molecules together. But life doesn't really stop there. I'm sure in your general chemistry book that you saw this plot. This is a plot of the enthalpy or heat of vaporization of different molecules as a function of their position. You would think this is a chemistry building, so there'd be a periodic table in here. But as a function of their position as you go down a column in the periodic table. And if we look at the oxygen series, oxygen, sulfur, selenium, tellurium, we see this very characteristic plot, which is mirrored by the halides and mirrored by the amines and its congeners. The first member of these series has an enormously high heat of vaporization relative to the subsequent member. And then the third member goes up, and the fourth member goes up. This is one of the reasons why we believe in the existence of what are called hydrogen bonds. It's to explain this strong energy that's not exhibited by the next member of that group of atoms, that family of atoms in the periodic table. The same strong energy exhibited by hydrogen when it's attached to oxygen, or hydrogen when it's attached to fluorine, and so on, also shows up in things like the melting points and the boiling points. This is due to strong hydrogen bonds forming between water molecules, between ammonia molecules, between hydrofluoric acid molecules when they're in the liquid state. That contributes greatly to the enthalpy of dissociating that interaction so that you can transfer that molecule from the liquid state into the gas state. And remember, in a gas state, the molecules are so far apart that essentially there's no interaction at all, because R to the 6 dependence. By the time you get to the density of the molecules in the gaseous state at room temperature and relatively low pressures like atmospheric pressure, the molecules are so far apart that the R to the 6 just dampens out all the interactions between the molecules. And hydrogen bonding interactions are even shorter ranged than R to the 6th. They typically don't persist even over a few angstroms. Where'd my, oh, here's the book. These plots that I just showed you showed up for the first time, at least first time I'm aware of, in this book, which I'll pass around. Don't abuse it. This is a first edition of Pauling's The Chemical Bond. As a graduate student, you must be able to say, I have put my hand on this book. I got this inherited through Professor Kolthoff, so please don't mess it up. It's historically very significant. But you'll see these plots in that book, and I believe they originated in Pauling's thinking. Although he certainly did not come up with the idea of a hydrogen bond. Chemists were pretty persuaded of the existence of hydrogen bonds in the 1880s and 1890s. It goes back that far. But we didn't understand the origin of them in terms of the basic chemical physics until much, much later. Certainly, quantum mechanics had to come into existence before we could understand it. Here's another interesting observation that's really important in chromatography, as you'll see later. If we look at the dielectric constant of a liquid, so this vertical axis is the dielectric constant. Now, to remind you, the dielectric constant is the characteristic of the liquid that governs the energy of separating two charged particles. The higher the dielectric constant, the lower the interaction between the two charged particles, versus the dipole moment. The dipole moment is a gas phase property. It's a property of individual molecules in the gas phase. The dielectric constant is a property of the molecules in the liquid state when they're much, much, much closer together. For simple, non-hydrogen bonding liquids, there's a nice regular relationship shown by the open circles between the dielectric constant of the liquid and the dipole moment of the gas. But when you get into molecules like water, like HF, like hydrogen peroxide, like methanol, like ammonia, there's a great deviation between these two properties, which is telling you that in the liquid state, there's something very different going on between the molecules than what's happening to the molecules in the gaseous state. The same kind of thinking helps us understand solid state chemistry. This is the structure of ice 1. This is not the ice in, what's his name's great science fiction book. What was that? Ice 5 or something like that. There's 4 different known forms of water ice, depending upon temperature. And they have somewhat different structures. But in ice 1, you will see that every single H is pointed at a lone pair of one of the 2 lone pairs of electrons on oxygen. And so every hydrogen bond that can possibly form is formed. That tells you something about how strong these processes can be. This is the structure of crystalline alcohols. So methanol, ethanol, propanol. When they become a crystal, each OH group is aimed at an oxygen. And every hydrogen bond that can be made is made in crystalline ice. In crystalline alcohols. So that the solid is essentially a polymer. In fact, if you take an alcohol and you put it in a low polarity, or at least put it in a solvent that doesn't accept or donate hydrogen bonds, what you see in alcohols is in solvents like that is cyclic structures. They're not linear. They tend to form cycles and pentamers and hexamers depending upon the concentration of the alcohol. Obviously, at infinite dilution, the alcohol is a monomer. But even at very remarkably low concentrations, like 10 to the minus 6 mole fraction, alcohols form these complex cyclic structures. They like to polymerize, if you will, in low polarity, non-hydrogen bonding media. You put them in something that can hydrogen bond, and it breaks up their ability to interact with one another. This sort of thing is very important in chromatography, because what happens when we start getting intermolecular interactions between the same species in the stationary phase? The partition coefficient is no longer constant. And if the partition coefficient is not constant, you're not doing linear chromatography. If you're not doing linear chromatography, you get crummy peak shapes. You get peaks whose retention time changes as you change the concentration of the analyte. So this kind of chemistry is very important in chromatography. Now, hydrogen bonding is only one example of what we call a donor-acceptor process. Probably the most generalized form of a donor-acceptor process is what we refer to as Lewis acid-base interactions. And what I'm going to talk about in a few minutes is how we chemically quantify heats of reaction when a Lewis acid reacts with a Lewis base. So let's go back to real fundamentals here and remember what a Lewis acid is and what a Lewis base is. By the way, in a Lewis sense, an acid is an acceptor and a Lewis base is a donor. Okay? So an acid is an electron pair acceptor and a base is an electron pair donor. So the acid is bringing the electron pair to the party, and the base has some vacant orbitals, some unfilled valency that it wants to get occupied by that pair of electrons on the acid. The Lewis definition of acids and bases subsumes the simple acidity that we're used to talking about, like Bronsted acidity. In Bronsted acid-base system, an acid is a what?
H plus donor.
That's yes, it is a hydrogen ion donor, and a base is
OH minus donor or H plus acceptor.
It's an H plus acceptor. And I did this deliberately because the language is bass-ackwards. Because when we talk about a Bronsted acid, it's a proton donor. You said an H plus, so it's a proton. And a base is a proton acceptor. And Lewis switches acceptor and donor because it's an electron pair acceptor and electron pair donor. So don't get confused by that. Another important distinction is, let's suppose we have a simple monoprotic Bronsted acid. What is it that characterizes the strength of its acidity? What parameter characterizes the strength of the acidity? You all had general chemistry. You all had analytical chemistry. What?
Stability of its conjugate base.
Now, what parameter, what quantitative parameter characterizes the strength of an acid, a Bronsted acid?
pH.
What?
pH.
K.
All right. Characterizes a particular solution. What characterizes formic acid as a stronger acid than acetic acid?
Ka.
K.
It's Ka. And that's it, right? That's all you need to know about an acid in terms of its Bronsted proton donating ability, is its Ka. And what do you need to know about a base?
Kb.
Kb.
Kb. And that's the end of the story. Unless it's a diprotic acid or a dibasic base, then you need Ka1 and Ka2, Kb1 and Kb2. But there's only one parameter that characterizes the strength of an acid in the Bronsted system, and one parameter that characterizes the strength of a base in the Bronsted system. But it turns out that this doesn't work when we start talking about Lewis acids and Lewis bases. It was found quite some time ago that a Lewis acid, and here are some typical Lewis acids: iodine, boron trifluoride, phenol, hexafluoroisopropanol, one of my favorites, and chloroform, are all Lewis acids. You actually require two separate parameters, Ca and Ea, to characterize an acid. And concomitantly, To characterize a Lewis base, you need two parameters, CB and EB. We'll get into the meaning of the C and the E in a minute. The reason they know this is that I can't tell you how many graduate students over how many years set about measuring the heats of reaction of various Lewis acids with various Lewis bases. And when they attempted to rationalize those heats of reaction, so we're talking about an acid and a base reacting to form some sort of chemical species which is distinct from the acid or the base. What they found out that they had to do for the heat of reaction is they needed to take the C parameter of the acid and multiply it by the C parameter of the base, and add to that the E parameter of the acid multiplied by the E parameter of the base. In other words, each acid is characterized by two rather different parameters. You need two kinds of acidity to define the total acidity of a molecule. And you need two, in the Lewis meaning of acid-base chemistry. And you needed two kinds of parameters to define the basicity of a Lewis base. If we drop either, we could drop either the Ca or the Ea or the Cb or the Eb, you can't correlate the heats of reaction anymore. It doesn't work. It's not the same as Bronsted at all. There's two different processes involved. The C parameter comes from covalent. And the E parameter comes from electrostatic. Covalent means the actual sharing of a pair of electrons. The electrostatic refers to the transfer of charge from one molecule to the other molecule. So this is frequently also called a Coulombic interaction, a real Coulomb's law kind of contribution to the net energy of the formation of the bond. This is really not a radical idea. We frequently represent bonds in terms of covalency, and also a Coulombic contribution to the net bond formation energy. Now another great inorganic chemist, Ralph Pearson, went through these tables of data, and he came up with the chemical characteristics that differentiate acids. He used slightly different language than the first people, led by Russell Drago. He referred to the acid as having hard characteristics and soft characteristics. The hard corresponds more to E, and the soft corresponds more to C, covalency. And he said that hard acids, let me back up here a minute. You should not think that the word hard means strong. And you should not think of the word soft as meaning weak. It's like they could have called them red and green, but they called them hard and soft. It can get a little cumbersome. They're different kinds of acidity. And you can have a very strong hard acid, and you can have a very strong soft acid. It depends upon these parameters that I just showed you over here. Things that have big C parameters have a high covalent contribution to the EA bond formation. Things that have big E parameters have big electrostatic contributions to the bond strength. And similarly for bases. And you can see there are really big differences here. For instance, I also need to explain one other thing. In order to measure these numbers, he had to choose a reference acid, okay? And a reference acid for the coulombic and a reference acid for the electrostatic, and he chose iodine. And so by definition, the Ca for iodine is 1.00000, and the EA parameter for iodine is 1.000. And given that now, everything is really measured, the heats are now all measured relative to the iodine acting as an acid towards some base. And all the others are relative to that. So once we define those two, we can then quantify all the others from measurements of the heat of reaction. So Pearson, in looking at these things, he says, aha, these hard acids, the acids with a big electrostatic parameter, they tend to be small, they tend to have a high positive oxidation state, they have no easily excited outer electrons. This is easy to understand if you just think about the representative species. There's not much smaller than a hydrogen ion, okay? And it's very difficult to get hydrogen atoms into an oxidation state greater than 1, plus 1, right? It's got no more to lose in terms of electrons. It's gone. Lithium, very small. Aluminum, if we had a periodic table up there, you'd see it's at the top of its row. The top of its column. And aluminum in a +3 state. Maybe some bizarre inorganic chemist like John Ellis has gotten it into a higher oxidation state, I don't know, but aluminum-3 is about where aluminum's at. These are all very, very good, hard Lewis acids. Opposite the hard is the soft. The soft species, the things that are soft acids, they tend to be larger. They tend to be in a low positive oxidation state, and they have lots of easily excited outer electrons. Representative of soft acids are things like silver 1, mercury 2, thallium 1, copper 1. You'll see in a second that these hard acids tend to react most strongly with hard bases, and the soft acids tend to react most strongly with soft bases. So shifting over to bases, the hard bases are species that have a low polarizability. They have a high electronegativity. They're difficult to reduce. They're already in the lowest oxidation state you can get them in. And they have rather inaccessible high energy orbitals. Very representative hard bases, hydrogen ion. And what reacts best with hydrogen ions? I'm sorry, what did I say? Hydroxide ion. What reacts best? In water. It's the strongest possible base in water, right? But things like fluoride, water, and oxide ion are also very, very hard Lewis bases. And obviously, you put oxide ion in water, it immediately reacts with the water, and you get hydroxide ion. The soft bases have a high polarizability, a low electronegativity. They're easily reduced species, and they have easily accessible orbitals. And these include things like I- ethers, olefins, anything with pi electrons, benzene, sulfides. Sulfides are really, really soft bases. Now, if you remember any of your descriptive inorganic chemistry, silver ion reacts with fluoride, chloride, bromide, and iodide, right? Which solubility product is lowest, meaning it's the least soluble silver halide? You don't remember?
Silver iodide.
Iodide. Silver iodide 10 to the minus 16. Silver bromide 10 to the minus 14. Silver chloride 10 to the minus 10. Now this stuff was not derived from those solubility products, but it predicts them very well. It predicts very well what metals will bind to what kinds of anions, what complexes will form between copper and ammonia. Ammonia is a rather soft base. It should be on that list there. And this stuff all comes into play when we start doing chromatography. As an example, in normal phase liquid chromatography and even in gas chromatography, people will add silver ions to the stationary phase to induce strong retention of species that have easily polarized electrons. So if you want to separate aromatic molecules from aliphatic molecules, you get a silver impregnated phase. It's going to it doesn't do a thing for the saturated molecules. It just doesn't retain them much. But it goes after olefins, it goes after aromatics like crazy, and they're much more strongly retained than are the corresponding alkane in the presence of the silver. In the absence of the silver, in GC it's more of a boiling point separation because this interaction is completely missing. A couple of years ago, I read a really excellent paper by some people in food science who wanted to separate different kinds of carotenoids from non-carotenoid molecules. Well, carotenoids, I may be misremembering, but it's like 30 carbons long, and it's double bond, single bond, double bond, single bond, double bond, single bond, and so on and on. I mean, it's what hyperconjugated, and the silver impregnated normal phase just sucked the stuff up and gave a gorgeous separation of the carotenoids from almost everything else in the mixture. It's just chromatographic applications of this kind of chemistry. So the point is, if you know the chemistry, you can do things that you can't do if you don't know the chemistry. So it's very important to be familiar with this stuff. Getting into biochemistry a bit, there's been a lot of work with what people call metal ion affinity chromatography, where they deliberately bind to the stationary phase certain inorganic metals to fish out of solution different biomolecules that have different functional groups. So for instance, if you wanted to fish out a protein that had a high sulfhydryl content, that is, the protein had a lot of cysteines in it, the way to go is to put something like silver or copper 1, and it will interact with the thiol groups and the sulfur groups in that protein rather selectively. If you have a protein with a lot of bases in it, that basic amino acids, the dibasic amino acids and so on, like imidazole, then you want to hang in there with some copper 2, not copper 1, zinc, iron, nickel, cobalt, and it will fish out the proteins that have lots of imidazoles and lots of lysines in them. In fact, in genetic engineering, it's very common to hang on what's called a leader sequence of 4 or 5 histidines, and then fish that protein out of all the others. When I say 4 or 5 histidines, I mean it's the first 5 amino acids in the chain would be histidine. Something like iron 2 would go in and just grab that stuff and let almost every other protein just float on out of the column. And then you add a lot of histidine to the mobile phase, outcompete the stationary phase, it comes off the stationary phase and out comes the protein that you want. If not perfectly pure, a heck of a lot purer than it went in. So this kind of chemistry is very exploited in doing chromatography. Perhaps more so in LC than in GC, but definitely people have put silver and mercury predominantly into GC phases to fish out things with pi electrons in them. And even halides like iodides, because iodides are so polarizable, they will hang up on the silver. I really just scratched the surface here, because I mean anything you can think of that organic chemists or inorganic chemists have done in terms of charge transfer, complex formation, we're going to try and exploit that one way or another as chromatographers. It's a very important area. I wish it were better understood, but that's where it is right now. I think I'm going to start the next topic and go a little bit further before giving us a break. I'm gonna start by being a bit of a skeptic. I think it was Joel Hildebrand who said that you should never believe any simple model about liquids. And Hildebrand spent his life studying liquid state and in fact originated solution theory, regular solution theory. Its value is it is simple, and it makes qualitatively correct predictions and even semi-quantitative predictions about mixtures and about interactions that we can exploit in chromatography. Has anybody ever heard of regular solution theory before? Has anybody studied theories of solutions before? That's because physical chemists are enamored of the gas state, where almost nothing interesting happens. Certainly no biochemistry. I'm sure you've all seen this equation before. I know you have because you've studied mixtures of ideal gases. And this is what happens if I take ideal gas 1 and ideal gas 2, different amounts, different numbers of moles of them, and mix them together to form an ideal gas mixture. The free energy of this mixture, of the total mixture, depends upon the number of moles of species 1 and the standard free energy of species 1 plus the number of moles of species 2 times the standard free energy of the free energy of formation of that species plus these two terms, which represent the entropy brought into the mixture. Because you're forming a mixture inherently has a greater entropy than does a pure gas. And we can simplify this a little bit and put it into a form which I know you've seen by looking at the definition of the mole fraction. And we're going to stick with binary mixtures today. So I'm going to substitute x1 equal to n1 over the sum of n1 plus n2 for this. And x2 is going to be n2 over the sum of n1 plus n2 for this. So that's your free energy of an ideal gas mixture. Now, if you have a liquid that forms an ideal mixture, it will follow exactly the same equation. But I said if, because finding liquids, mixtures that are absolutely ideal is really hard. What's the biggest difference between what's going on in a gas, a pure gas, and the pure liquid of that gas? What's the difference? Are there any interactions, attractions between the molecules in the gas phase? If it's an ideal gas?
No.
Absolutely not. Otherwise it won't be an ideal gas. So the problem with a liquid is there are interactions between the molecules in the liquid. And if we form a mixture of two liquids, the interactions of one with one, and one with two, and two with two are not necessarily exactly the same. But if they were exactly the same, then they would follow this relationship that governs any ideal mixture. So to form an absolutely ideal liquid mixture, molecules of type 1 cannot tell the difference between molecules of type 1 and molecules of type 2. In other words, for this molecule of 1, it doesn't care whether the next molecule over is either 1 or 2. It has the same energy, it has the same free energy. And vice versa. A molecule of type 2 doesn't care if the next molecule over is 1 or 2. It's just as happy in either case. The only way I can see this coming about is if, and it's not quite true, is if we have a mixture of two isotopes. Like if we had liquid bromine, and I forget the atomic weights of the isotopes of bromine, but if we had bromine of one isotope and bromine of another isotope and mix them together, or if I had benzene that had 6 hydrogens and benzene that had 5 hydrogens and 1 deuterium, they would come close to forming an ideal liquid mixture, and they would obey this equation. So you get the idea of an ideal mixture? Okay, now we get on to the title here. What is the excess free energy of mixing of a real liquid? This is simply a definition. Whoops, oh there, I'm sorry, I should have told you about the ideal entropy of mixing, and it's simply minus R sum Ni log Xi, and you can easily calculate that from this by simply taking the temperature derivative. The excess energy of mixing is the energy that you observe, the free energy that you observe when you mix them together, and then you subtract off the ideal free energy of mixing. So the excess is the energy the free energy over and above that which the ideal mixing equation predicts. So the smaller this number is, the closer the mixture is to being an ideal mixture. That makes sense? And keep in mind, this is a pure component thing, and this is the only thing that has to do with a mixture. Okay, now we get to regular solution theory. And the people who developed regular solution theory, they came up with what they found was a very useful definition of not an ideal mixture, not a real mixture, but a almost ideal mixture. And they said the following. They said that the excess entropy of mixing is zero. The excess entropy of mixing is zero. What this means is that the mixture is perfectly random. The only way the excess entropy of mixing is going to be zero is if a molecule of type 1 does not know what is around it. That there are no interactions between 1 and 2 which are different than interactions of 1 with 1. And vice versa. A molecule of 2 doesn't know that it's got molecules of type 1 around it, or it's got molecules of type 2 around it, or any combination thereof. So the 1-1, 2-2, and 1-2 interactions have to all be the same. In which case, what will be around any given molecule will be just a random mixture. So that's part 1 of the definition of a regular solution. Part 2 is the excess volume of mixing is zero. Now this one's a lot easier to understand, thank goodness. If I take 100 mLs of liquid 1 and 100 mLs of liquid 2 and pour them together, and if I wind up with exactly 200 mLs, there's no excess volume of mixing. There's no volume change upon mixing. This now allows us to find out something very simple. Here's the excess free energy of mixing in terms of the excess enthalpy of mixing and the excess entropy of mixing. And I can set the enthalpy equal to the energy of mixing plus P delta V excess minus T delta S of excess. Now, if the excess entropy is zero, that goes away. So that goes away. And if the excess volume of mixing is zero, that goes away. That leaves us with this wonderfully simple situation. The excess free energy of mixing is equal to the excess enthalpy of mixing, which is equal to the excess energy of mixing. So, if I can come up with an equation for that, then that immediately gives me an equation for that. And since it's the free energy that really matters in chemistry, right? Enthalpies don't really matter. Not really. We come up with the big kahuna. We get an equation for the excess free energy of mixing. Now, since the excess is equal to the real minus the ideal, I can get the real free energy by simply adding the ideal entropy of mixing into my estimate of that, and I now have an equation for the real free energy of mixing for a pair of liquids that obeys the regular solution model. But both of these things have to be true. You have to obey both the excess entropy of mixing is zero and the excess volume of mixing is zero. Are these things always true? Hell no. Are they true in a lot of cases? Yeah. Okay, so what do I mean by an ideally random mixture? Okay, so there's molecule type 1. And suppose I form a mixture of one molecule type 1 with molecule type 2. And let's suppose that it's 20 mole percent 1. So mole fraction of 1 is going to be 0.2. And the mole fraction of 2 is 0.8. Well, in this mixture, on average, each molecule of type 1, that's that guy, on average, would be surrounded by 4 molecules of type 2 and 1 molecule of type 1. Because the interaction of 1 with 1, 1 with 2, and 2 with 2 are all identical. Think about the mixture of isotopes. And in the same mixture, molecule of type 2, on average, would have the same kind of distribution. In a 50-50 mixture of 1 and 2, a molecule of type 1 would have 50% of its neighbors, on average, would be type 1, and 50% would be type 2. A molecule of type 2, 50% would be type 1, and 50% would be type 2. That's a random mixture. It's a mixture where the neighbors are in direct proportion to the fraction of the total, which is that species. Believe me, this is related to what we're talking about. So let's imagine I got 2 ideal gases. Do they always, ideal gases, do they always mix? Yes. Gases mix in all proportions as long as they're ideal. At higher pressures, lower temperatures, gases don't always mix. In fact, you get into the realm of supercritical fluids, which is gases at lower temperatures and higher pressures. You find lots of things that don't mix together completely. For instance, you can have supercritical carbon dioxide with methanol in it. If the methanol is kept at fairly low concentrations, it mixes, but you go above a certain amount of methanol, get 2 phases. They don't always mix, but ideal gases always mix. Why?
No interaction.
There are no interactions, so the only driving forces are the entropy. I don't know if you can really legitimately call entropy a driving force. It doesn't feel right to me, but the driving force for mixing is the entropy that you get when you combine 1 with 2 that's not there when you have pure 1 and pure 2. So that entropy will always give you a negative free energy, and voila, you got a mixture, and it doesn't matter what the proportions are. Should liquids in general always mix? No, hexane and water don't mix. Why? Because the interactions of hexane with hexane are nothing like the interactions of water with water or the interaction of hexane with water. The more dissimilar those interactions are, quantitatively dissimilar they are, the less soluble in one another those two liquids are going to be. But, if I contact water with some hexane, or vice versa, if I contact hexane with some water, and I let it come to equilibrium, will there be any water in the hexane?
Yes.
There will be. Why is it there if water doesn't like hexane and hexane doesn't like water?
Entropy.
Entropy is completely, that presence is driven by the entropy. Entropy, you can't beat entropy. It will always win, to some extent. If you go to Las Vegas and stay there long enough, you'll come home broke. It's the same law of nature. Okay, now. So, in regular solution theory, what we need to do is come up with a model for the energy of mixing. And once we have the energy of mixing, we're home free. We got the delta H of mixing, we got the delta G of mixing. So that's the next step in the regular solution theory. Okay? So let's take a break here. Let's do 10 minutes. So at 6:40, we'll reassemble the mixing equation. This is not hard to derive, it's just tedious, and I go through the description of where it comes from, but basically, this is the volume fraction of liquid 1, and this is the volume fraction of liquid 2. And so it's considered to be a random mixture according to volume fractions as a measure of amount, not mole fraction as a measure of amount. And if so, and given that delta S of that excess delta S of mixing is 0 and excess volume of mixing is 0, then you can get to this equation where delta E1V is the energy of vaporization of pure 1. Okay, so the opposite of that, if you take pure 1 gas, ideal gas, and condense it, you're going to get that much energy. So if you take that amount of pure 1 and put it into a mixture, that's going to bring in that amount of energy. And similarly, for species 2, we're going to get that much amount of energy brought in by the 2-2 interactions. Now, in the mixture, you have something that is not present in the gases. You've got 1-2 interactions, and so we have to bring in this term to represent the interactions of 1 with 2. Because they form in the mixture, they're not present in the pure liquids. The trick, if there is a trick in regular solution theory, is how do we come up with that number? And it's a very important part of the problem. And what's done is to look at the various equations I presented earlier about dispersive interactions, about dipole-dipole interactions. And if you look at how they combine when you're talking about interaction of 1 with 2, most of them, not all of them, follow what's called a geometric mean mixing rule. And what that means is we take the energy of the 1-2 interactions to be the geometric mean of the energy of the 1-1 interactions times the energy of the 2-2 two interactions. So we say that this energy is the square root of the product of the two pure interactions. Now this is very interesting, because ultimately what it means is we will be able to measure the energy in a mixture knowing only the properties of the pure substances. That's a huge arithmetic simplification. Is this always true? It can't possibly always be true. Let me go back to my friends hexane and water. The interaction between water molecule and a hexane molecule, it can't conceivably be the square root of the water-water interactions times the hexane-hexane interactions. They don't interact even by the same kind of forces. The dominant, not overwhelmingly dominant, but certainly a hugely significant interaction in water is what? We just beat it to death a few minutes ago.
Hydrogen bonding?
Hydrogen bonding. Is there any hydrogen bonding involved in hexane interacting with hexane? I think Pauling would turn over in his grave if he heard that was true. So this certainly is not always true. Is it good for certain kinds of mixtures? Hell yes. Hexane interacting with heptane is awfully close to the square root of the interaction of hexane with hexane and heptane with heptane. That's not a bad approximation. If we make that approximation and stick this equation in there, voila, no cross term anymore. The only thing we're dealing with is this, which is a pure, is a property of just component 1, and this, which is a property of just component 2. And then the molar volumes of 1 and 2, and the number of moles of 1 and the number of moles of 2. So we've estimated this energy of mixing, which is equal to the enthalpy of mixing, which is equal to the free energy of mixing, actually the excess free energy of mixing. And if we want the real free energy of mixing, all we have to do is add back in the term representing the ideal mixture. And you got the real free energy of mixing. If all of these assumptions and approximations are true, being the excess entropy of mixing is 0, excess volume of mixing is 0, and the energy of mixing of the 1 upon 2 or 2 upon 1 obeys the geometric mean rule, then that's the answer. So you need 3 things for this to be true. If any one of them breaks down, you got a problem. Okay, now, this ratio of energy to volume, or energy of vaporization to volume, appears so many times in these equations that your hands fall off writing it over and over and over. So they have introduced this terminology. They represent that ratio, the square root of that ratio, as a number called the solubility parameter. It's a characteristic of the pure substance. How do you get it? You measure the real enthalpy of mixing. It's a property of the pure substance. You take the pure substance and you vaporize it and you measure that enthalpy. Since you want an energy, you have to correct for the volume change. Assuming it's an ideal gas, that volume change is essentially RT, because the volume of a liquid is minute compared to the volume of an ideal gas at the same temperature. So this is easily measured. This, of course, is trivially calculated. You have to measure the molar volume of the substance. Not too hard. Take the square root, and you have the solubility of the particular compound. This is called the solubility parameter. It's also called, this delta is also called the cohesive energy. In other words, the amount of energy holding it together as a liquid relative to the ideal gas state. Density. It's a density because it's per unit volume. Density is mass per unit volume. Cohesive energy density is the energy of vaporization, the cohesive energy divided by the molar volume. Here is numbers for all kinds of liquids. The world record, if you will, in low polarity is owned by the perfluorinated alkanes. They are very low polarity. They don't even mix with hydrocarbons. So perfluorohexane and hexane don't mix well. Its solubility parameter 5.9. Here's hexane 7.3. That's a fair gap in cohesive energy densities. These are the molar volumes. Perfluorinated molecules are always a good deal bigger than the hydrocarbon analogy because fluorine is a kind of chunky atom. So it does make the molar volume go up. Let's look at something like acetonitrile. Acetonitrile has a rather higher solubility parameter because it certainly has dispersive interactions, but it also has dipole-induced dipole interactions, and it has dipole-dipole and dipole-induced dipole interactions, or polarizability interactions. And then something like water with the super high value, and I don't know if anything is actually higher than water, 23, that's got an awful lot of hydrogen bonding contribution to its cohesive energy density. This also happens to be a fairly small molecule. So this spans a very, very wide range in liquids and a very wide range in solubility parameters. Okay, so what? What good is it? Well, it turns out that, again, the basic theory tells us that we can predict activity coefficients. So here's the activity of compound 2 in a mixture of 1 and 2. That's the activity coefficient. So RT ln gamma 2, that's actually the free energy of putting 2 into solution in 1. That depends on the molar volume of species 2. It depends upon the volume fraction of species 1. And it depends upon the square of the difference in the solubility parameters of 1 and 2. There's no parameter representing the interaction of 1 with 2. That came from the geometric mean rule. That's why it's not there anymore. Now, the volume fraction is calculated as the mole fraction times the molar volume of that species divided by the total volume of the system. Let me make life simple and only consider a binary mixture of 1 and 2, not 1 with 2 and 3 or anything more complicated. And let me go to infinite dilution of species 2 in liquid 1. So if I make phi of species 2 equal to 0, then phi of species 1, if I make that 0, then the mole fraction of species number 1 has to be 1. So this becomes 1. And we now have the infinite dilution activity coefficient of species 2. What good is this? Where have you seen an infinite dilution activity coefficient before?
Beta,
Hmm?
beta, for instance.
Yep. Beta for gas chromatography. Is that? That's a property of the pure solute. It's just the vapor pressure of the pure solute at the column temperature. That's the molecular weight of the stationary phase. Has nothing to do with the solute whatsoever. That's the infinite dilution activity coefficient of the solute. That's the species at infinite dilution in solvent 1. That's the stationary phase. So if you can get that number and get that number, you now have the whole ball of wax for gas chromatography. You can now, in principle, calculate the partition coefficient, and then, of course, you can calculate the retention volume. So, if I had a big enough table of these properties, I could calculate the partition coefficient of any solute in any stationary phase that I had the delta for. Polymer chemists want to figure out how polymers mix together. Same exact equations are used by polymer chemists for figuring out whether polybutadiene will be soluble in hexane or not. The same exact theory. There are huge tables of these numbers that come from all kinds of technologies you wouldn't imagine. Okay. So, let's take a look at that equation in a little more detail. So we're going to be looking at it, we're going to break up this equation for log gamma. In fact, let's just do it for the infinite dilution log gamma. There's really three terms on the right-hand side here. If we work out that square, and each of these terms has a physical meaning. Okay, so when we're talking about the activity coefficient of compound A at infinite dilution in solvent B, the net process involved here is we start with pure liquid A. We take a molecule of A out of pure A and we transfer it into a dilute solution in B, which means that A is completely surrounded by B. So there's really three things we have to worry about here. We have to worry about breaking the interactions of A with A. That's this step. Now consider that we've assumed that there's no volume, there's no excess volume of mixing. That means that we have to figure out how to create a space in the B liquid to put the A. So we actually have to think about breaking some B-B interactions here. And then we can slide this A molecule into the C of B's, and we're going to make A-B interactions. So there are 3 different intermolecular interactions involved in the mixing of pure liquid A into pure liquid B at infinite dilution of A and B. And that's why there are 3 terms over here. Sorry, I'm getting my A's and B's mixed up, but I thought it was better to do A and B in the lattice thing than it was to do 1s and 2s. But this would be the A. That would be the B. So V naught A, delta A squared, that's the energy of getting the A out of the pure A into the gas phase. V naught A times delta B squared is the energy of creating the space in the B liquid to fit the A molecule. So that makes sense that that depends upon the size of the A. If the A were really tiny, it wouldn't require creating such a cavity or gap or whatever you would want to call it in the receiving solvent. And then the middle term is the energy that we get back by forming the A-B interactions. Now, the square of a number is always positive, right? So this has got to be a positive quantity, that's got to be a positive quantity. These contribute 2 unfavorable terms to our energy, 2 unfavorable terms to our enthalpy, and 2 unfavorable terms to our free energy. Breaking the AA interactions and breaking the BB interactions are unfavorable and vigorously oppose the solubility of A and B. What drives the solubility of A in B is 2 things. It's this energy which is liberated when they finally come in contact with each other, and entropy. You guys all intend to take oral exams someday? Yeah. I'm going to tell you a secret. When they ask you a question and you have no idea what the answer is, it's one of 2 things: entropy or resonance. Half the time, I've got it right. Okay, so what drives mixing of A with B is the energy of the A-B interactions that you form when you make the mixture, and the fact that you've got a mixture and you have increased the entropy of the system by forming that mixture. But the price you pay is you're breaking some AA interactions and you're breaking some BB interactions. And the stronger those AAs and BBs are relative to the AB, the less soluble the stuff is going to be. So, obviously this side of the equation, unless you believe in negative volumes of species, this side of the equation has to be positive, right? You've got to be positive. It's a square. That means that RT ln gamma is positive number. If we take the anti-logarithm, what that means is that regular solution theory predicts always that the infinite dilution activity coefficient is always greater than 1. That ain't always true. If the A-B interactions are really asymmetrical enough that hydrogen bonding, what have you, you can have activity coefficients that are a good deal less than 1. It can happen. That means that the regular solution theory, one of our assumptions, is breaking down. And it's probably the geometric rule approximation that's breaking down. So, before I get to the end here, it's extremely important in understanding gas chromatography and liquid chromatography to think about the energy of the cavity formation process. But let's suppose I've got a gas, I've got a solute in a gas phase, and I want to stick it in a solvent. This is a gross, absurd cartoon because the shape of the solute molecule is not going to be the same in a gas phase and when it's in a liquid state. And in addition, these things have rotational energy, so it's absurd to think of its shape as being an L. But you have to create a space in the solvent to accept the solute. You've got to push solvent molecules apart. And the bigger the solute molecule is, the less soluble it's going to be, simply based upon that cavity formation process. This will go a long way towards explaining some of those trends I showed you on the last slide the other day, where we looked at 4 different molecules in 4 different related stationary phases for GC, going from hexadecane to pentadecanitrile to the hexadecanol to the I forget what ether it was. But those numbers were all over the place. And a lot of those differences in behavior are due to the energy of cavity formation. You cannot dismiss that. It's a very vital factor. Okay, so consequences of regular solution theory. Mixing is always endothermic, unfavorable. Activity coefficient is always greater than 1. A solute always tries to escape from a dissimilar solvent, according to regular solution theory. And if we really believe the equations, it makes this final ridiculous prognostication that the log, the ratio of the infinite dilution activity coefficients is given by nothing other than the size of the 2 molecules. So this is the activity coefficient of species 2 in 1, and this is the activity coefficient of 1 in 2. If you take those equations and put them together, the delta 1 minus delta 2 squared drops out. And how can that be? That just doesn't make any sense unless all of these approximations, all of these assumptions are dead on. So I'm not making any claim that regular solution theory applies to everything. But it applies to a lot of things. It applies to enough things that there are 2 papers that I want you to read. It's the papers by Snyder, Karger, S-N-Y-D-E-R, Karger, K-A-R-G-E-R, and Eon, E-O-N. If anybody speaks French, you will forgive me. I don't do French very well. It's two papers where they take the basic equations of solubility parameter theories and derive the retention factor in gas-liquid chromatography, gas-solid chromatography, liquid-liquid chromatography, and liquid-solid chromatography. They have pulled all of chromatography together and predict retention. Does it work accurately? No. Does it make reasonable predictions? Yes. But you got to have the deltas, and you got to know how big the molecules are, and that's all you need to know. And I just want to go. This is for mixed solvents. That is, if I have, and frequently in chromatography we do mixtures of solvents, like in reverse phase chromatography, water and methanol, water and acetonitrile, water and tetrahydrofuran, and we put a solute in it. But this is the equations that work out. I gave you that because this gives me an equation that I can apply to chromatography. And I'm going to emulate reverse phase chromatography, where the mobile phase is very polar, like water, and I've added some methanol to it. And the stationary phase is very nonpolar, like hexadecane. So I'm using a water-methanol mixture for that. I'm using hexadecane for that. And I'm going to think about a number of different solutes. This was supposed to be an I, and that was supposed to be an I. So this is my final equation for liquid-liquid chromatography. It's very easy to derive from regular solution theory. This is my partition coefficient for liquid-liquid chromatography. And I'm going to calculate the log 10 of my partition coefficient as a function of the volume fraction of methanol in methanol water. And I'm going to use hexadecane as the model of the stationary phase. And my solutes are going to be benzene, toluene, ethylbenzene, propylbenzene, and N-propylbenzene, and N-butylbenzene. And I can look up the solubility parameters of everything I just listed. Here's benzene. What this is telling me is that as I add methanol to the water, I should expect to see the partition coefficient into hexadecane go down and down and down and down. What this means is that as I add methanol to water in reverse phase chromatography, retention should go down and down and down and down for benzene. It does. If you look at the plot, it's almost linear. And in fact, the decrease versus the volume fraction of methanol is almost linear in reality. It predicts as I go from benzene to toluene, and toluene to ethyl, and ethyl to propyl, and propyl to butyl, my partition coefficient should get bigger. That means toluene should be more retained than benzene, etc., etc., etc. Does this happen? Yes, this is exactly what happens. It's also predicting that the slope of this should be bigger than the slope of that. Does that happen? Yes, that happens. I can predict a lot of qualitative aspects and rationalize them of reverse phase chromatography using this extremely simple theory. Is it quantitatively accurate? It's off by orders of magnitude. Water, methanol, and hexadecane do not form simple random mixtures. It's just not so. But it's nonetheless a very qualitatively useful theory for figuring out the direction of changes. Okay, let me get in the beginning of my next lecture. I don't want to give up too much time. So, we're starting into a discussion of HPLC now. And it's going to take us a number of weeks to go through HPLC because there's instrumentation issues, there's chemistry issues, and then there's a whole bunch of different kinds of HPLC. Basically, GC, there's gas liquid chromatography and gas solid chromatography, and that's it. In liquid chromatography, we got normal phase, we got reverse phase, we have ion exchange, we have bioaffinity chromatography, we have chiralchromatography, we have metal ligand exchange chromatography. You can do a lot more with liquids than you can with gases. And it's why LC is so much more powerful than GC in general. GC is really only done on species that are volatile and thermally stable. They have to fit both of those criteria. And organic chemistry and biochemistry, there aren't that many volatiles and there aren't that many thermally stable if we're talking 200 or 300 degrees C. So LC encompasses a much bigger fraction of all the molecules that we know about than GC. Okay, we'll start real simple. Here's a basic isocratic LC system. Isocratic means we're not going to change the eluent, the mobile phase, during the run. We got one liquid, it may be a mixture, but we're not going to change the composition of that mixture during the run. So we got our solvent mixture here. We have a pump. You don't need a pump in GC. The carrier gas is under pressure, and that pressure just drives the gas through the column. We already know that the pressure drops in LC are vastly higher than in GC because liquids have much higher viscosities, and the particles that we need to put in the column are much smaller than in GC because mass transfer in liquids is so much slower than in gases that we need to compensate for that by using smaller particles. Because this is a higher pressure operation, you can't just take your sample in a syringe and stick it somehow behind the septum and squirt it, unless you can generate on your fingers 4,000 or 5,000 psi of pressure, which ain't likely, and it's not going to be reproducible. So we need devices to load the sample into the column. There's invariably a valve. We got our column, we have a detector. You can tell how old this slide is because I'm betting any number of you have never seen a real recorder. Not a computer emulating a recorder, but a real recorder. Okay, this is pretty primitive. This LC will get the job done sort of, but it won't get the job done very well because it doesn't take into account a number of problems. Whoops, that's not my next. I'll get to the problems in a minute. The key component of any HPLC system, perhaps the key component, is the pumping system. It's a problem because it's got to work at high pressure. You want it to deliver a very, very constant flow rate. The pump has to be pulse-free. And designing a pumping system that is absolutely continuous without pulses in it is a very difficult problem. I should say by high pressures I mean these days up to 10,000, 12,000, PSI. That's on the order of 1,000 bar. Wide-ranging flow rates. Very few pumps work well below 0.05 mLs per minute, except pumps designed especially for capillary liquid chromatography. And for analytical purposes, the top end is about 5 mLs per minute. You want the pumping system to be chemically inert. I wouldn't just say resistant. Sometimes you have to use acid mobile phases. You may want to use 10th molar strong acid, not chloride, because that will rot the heck out of any stainless steel, but nitric acid, for instance, or chloric acid. You might want to use a very basic mobile phase when you're doing ion exchange work. So it's got to be chemically very resistant materials. If they're polymers components, and there will be, you don't want those polymers to shrink and swell as you change the solvent. Ideally, you want to be able to use a fairly large reservoir of solvent so you don't have to keep making up large batches of solvent. And you want the pump to be able to deliver 5-10 liters if you're doing long runs. And you want it to be low maintenance. It's like you want a car that'll go 150 miles an hour, stop on a dime, accelerate in 10 seconds to 150 miles an hour, and low maintenance. You're going to have to give something up. I mentioned the injection valve before we get deeper into pumps. Basically, the valve is a very simple thing. In one position, the fluid from the pump goes through a slot in the valve and goes over to the column. While you're doing that, this other side of the pump is under low pressure conditions. So you can take a syringe and deliver your sample to this piece of tubing. Then you rotate the valve and the path is changed so that the pump is connected. You rotate this so that over here it shows the path, so that the pump now goes through the loop and the sample goes out that way to the column. And during this part of the operation, this is at high pressure. And during this part of the operation, this is where the high pressure is. Now, this is a valve that has to turn while there's maybe 5,000, 10,000 psi back pressure on it without leaking. That means you have very, very, very close tolerances. Those are very carefully machined materials. Okay, we go back to the isocratic system. We're going to make it a little more complicated. These columns don't last forever because you may be using an aggressive mobile phase. So sometimes what's done is to put in what's called a saturator column, or you could call it a sacrificial column. And you let whatever this aggressive eluent is rot this column, saturate the mobile phase with whatever is going to rot off of the column. We'll get into what that is later on. And bring the mobile phase to equilibrium. So now it's at equilibrium. There's no reason for the analytical column to, or much less reason for it to be hurt, because it's almost at equilibrium. So that's That's one issue. Another issue, oh, and by the way, it doesn't really matter what happens in this column here because the sample never goes through it. So this doesn't have to be a really beautiful particles and well-packed column. So it's a pretty cheap investment. The guard column is put in there. It's basically, the guard column is a very short, identical material to the HPLC column. All real samples have garbage in them. And some of the garbage is going to stick irreversibly to your stationary phase. The purpose of a guard column is it's going to capture this stuff that's irreversibly adsorbed, and you throw it away, you throw the guard column away every however many injections, 50, 100, if it's a really clean sample, maybe several hundred samples before the guard column gives up the ghost. It's also there to preserve the analytical column. In some of these, prices run $500 to several $1,000s for an analytical column. You don't want it to die because you've calibrated your method, and if you change your column, you've got to recalibrate. Could be days of work. Another thing is that pumps don't work well unless there's a certain amount of back pressure. And if you're using big particles in the HPLC column, you often have to put back pressure on the column to make this pumping system work properly. Here's a gradient instrument, and this is called a binary gradient because there's this solvent and there's that solvent. So we've got two solvents. So it's kind of limited because you can only mix two solvents. And this is called a high pressure binary gradient system because we have high pressure pump A and we have high pressure pump B. And they're both pulling a certain flow rate of liquid out of the reservoir, out of their individual reservoirs. And the fluid that comes out of here is at high pressure, and the fluid that comes out of there at high pressure. The amount of this solvent that we draw depends upon the flow rate of this pump, and the amount from this depends on what the flow rate is from this pump. So we have to have a device that controls the flow rate because we want to change the relative amount of solvent A and solvent B as we go through the run. So there has to be an electronic interface coupled to both pumps saying, pump A, I want you to go fast, then go slower. Pump B, I want you to start slow and then go faster. And by the way, keep the volume flow the same. The total volume flow the same. So that's a high pressure binary system. If you wanted a ternary system where it was all high pressure, you'd need to get another high pressure pump. And high pressure pumps ain't cheap. So there's another way to do complex gradients, and I'm just illustrating this with a ternary gradient system, but I think most commercial instruments are actually quaternary, meaning they can handle 4 liquids. And it's done in the following way. Oh, whoops, I forgot a very important component here. You don't have that in an isocratic system. Solvent A, solvent B, they come together. They better be really well mixed. You don't want pulses of A, then pulses of B, pulses of A, pulses of B. That's a disaster. They have to be very well homogenized before they get into the injector and before they get into the column. Okay. Now, this is a quite different system. We only have one high pressure pump. We're going to feed this high pressure pump with a mixture of our solvents. So that mixture has to go through a mixer before it gets to the high pressure pump. The way that we get the mixture is we have what's called a solvent selection valve. This is a valve with, if you've got 3 liquids, it's got 3 gates, three on-offs. And it's very rapidly switching between the 3, spending more time with the solvent you want more of than with the solvent you want less of. And the on-off cycles of the A, B, and C are controlled by this eventually is a homogeneous fluid. This is a cheaper way to go because you only have one high pressure pump. But it's a lot harder to get the mixers to work, for one thing. It's very tricky to make these valves really, really toe the mark and be open and closed for exactly specified periods of time. And they have to be opening and closing very rapidly so that you don't have big slugs to mix, but little tiny slugs to mix, because it's much easier to mix small volumes than it is big volumes. I'll finish up on what is undoubtedly the most common type of pump, which is a reciprocating piston pump. Okay, so basically we have a plunger. It's a rod attached to a motor, and the motor is an eccentric motor, so that as the motor turns, the rod will do this, go back and forth. And keep in mind this is high pressure, so the tolerances on the spaces here are really difficult to define. We also need to make a seal around the rod so that we don't have any leakage around the rod because of the high pressure. So we need seals, typically polymeric materials. And what makes this thing work are these 2 check valves. If you know any electronics, a diode only allows current to flow in one direction. A check valve is a fluid diode. It only allows the fluid to go in one direction. These 2 check valves are working in opposition, so that when the piston is moving in, displacing solvent from the interior of the pump, this upward check valve is open and the fluid goes that way, whereas this check valve is closed, not allowing the fluid to go that way. Now, when the pump strokes backwards, when it's going that way, this check valve comes up and allows fluid to go around the check valve, but this check valve is closed, and so fluid goes back this way. It doesn't get sucked in from the column. So it's like a pair of fluid diodes. The check valves have to have incredible tolerances, very tight tolerances, and you don't want them to get dirty, because if they actually get a particle, that the seals will not make, and your flow rate will be all over the place. Reciprocating pumps are relatively cheap. If you think of $5,000 as relatively inexpensive, then they're relatively cheap. They can get to very high pressures, like 1,000 bar, 1,200 bar. The bad thing about them is that the piston is doing this. Actually, I'm lying. The piston is not doing this. The piston is doing this. The backstroke is very fast compared to the forward stroke, but there will be a pressure pulse produced as you come back. And we have to do something about that. That's part of the technology. let's knock off for here. This is a good point to quit. Well, hang on one more second. This explains how the check valve works in a little more detail. In the open position, the pressure is pushing the check valve up against the spring. And in the closed position, when the stroke is going the other way, the spring is pushing the check valve down so that we can't have any flow in back of the check valve. So the flow is that way in this direction, and flow is that way, I'm sorry, flow is out in that direction, and then there's no flow in that mode. And the inlet check valve and outlet check valve work 180 degrees out of phase with one another. So one is open, the other's closed. Okay? You can see that these things are not trivial. And it doesn't sound that bad to me to spend $5 grand on a really good pump anymore. Okay. Thanks for coming tonight.